right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. I hope everyone is doing well. Get this thing set up here. In the meantime, I just want to mention that I'll be sending out okay, okay, no feedback. I'll be sending out some possible hours for office hours because I want you guys to meet with me in your groups, show me where you are with your project, sort of kind of a more hands-on kind of thing. Because I think some people or some students, when I kind of describe things in words, it's actually implementing them seems a little bit harder than actually understanding what I'm asking to do. So I figured that I'll just make some mandatory meetings, meet with each group, and I'll send out a schedule for that. I'm already meeting with a couple today, so I'll send you guys hours for next week at some point. So by early next week, I'll see everyone where you are, how far along you are, actually see what you've done, and maybe give you some suggestions. That being said, today we just want to go through a bunch of problems. This is from probability example set 2. And we want to do the rest of these problems. Don't know how many I'm going to get through. But last time we did problems 1, which was the Bayes rules, Bayes theorem, very famous type of Bayes theorem problem about having a deadly disease and the chance that you actually have the deadly disease given the effectiveness of some tests that you took. And we did that. You realize that the probabilities were actually very surprising, but when we actually sketched it out, it actually made total sense. And then we did problem 3 from that handout, where again we used Bayes' theorem, but we used version 1. This is called probability by conditioning. There is probably another way I want to talk about this, about doing this, which was actually mentioned in the last class as well, which I did want to do, but we ran out of time. So I just want to appreciate, we could also enumerate. As in like count one by one, because there are not many options here, right? It was possible for there to be many options, right? I could be like, well, imagine you're playing Dungeons and Dragons and they took the D4 and they changed up 3 sides, or they changed up the, right? And then you're gonna, you can't count it all, right? But here it's 2-sided coins. There are like 5 of them. It's not a lot to count, 10 things really, right? 1 for each side. And so you can actually enumerate them. So you'll be like, okay, so what would my sample space look like? Well, the sample space would consist of 5 coins: coin 1, coin 2, coin 3, coin 4, coin 5, right? And so coin 1 would have like, a heads and a tails. Coin 2 would have a heads and a tails. Coin 3 would have a heads and a tails. And then the remaining 2 coins are actually unfair. They have 2 heads. So the 4th head would be here, the 5th head, the 6th head, and the 7th head. So those were the options. And now you know you want the probability of getting heads. Well, total options. So here you'd realize that the size of the sample space is 10. There are 10 things. Sample space is 10 since a coin flip will give 1 of the options on the left. and I was numbering them, you can clearly see that 7 of those options are heads. 7 of these are, someone else is getting in here, are heads. Okay, there are 7 H's. So probability of heads is just the number of ways we can get heads, the size of the event we get heads, divided by the size of the sample space, number of ways you can get what you want divided by the total number of possibilities. And again, you can get 7 out of 10. So you could actually just count it. This one was small enough to count. It's not always going to be the case. So you probably should know this in case the numbers are large. But if the numbers are small, you could actually just write it all out, write out every option, and figure it out that way. Which, I mean, some students figure that out that way before I show them the conditioning. So let's actually do the rest of these. So we're going to start with the birthday problem, very famous birthday problem. And let me just kind of move these other ones out of the way. Now, if you recall, this was one of the probability teasers that I gave you guys. How many people have to be in a room for it to be likely that 2 people would share the same birthday? And I told you that the answer was 23, which doesn't sound like a lot. Because how many people would you need to be certain that 2 people shared the same birthday if you assume that a year has 365 days? Well, there's a principle called the pigeonhole principle that tells you, well, 366 people. So you'll need 366 people to be 100% sure that 2 people share the same birthday. So you might think that, oh, we'd have to get like halfway there. We'll need like 150, 200 people before we can be sure that, before we can be confident that, 2 people share the same birthday. It turns out the answer is no. You only need 23 people. Once you have 23 people, there's more than a 50% chance that 2 people share the same birthday, which is interesting. Now, this class is super small. Normally, when I do this in an 1108 class in person, the classes are usually a lot larger, 25 to 30 people, and I actually have them go around and say their birthdays. And yeah, so far I've always had a match, like every time. So this class is way too small to try that. We could probably work out the probability that anyone in this class shares the same birthday, but it's going to be small. But it turns out with 23 people, you can get more than a 50% chance. So let's see how. A. Okay, so we're assuming a year has 365 days. So here's what we can do. Since repeats can occur, let us order the people and use tuples. i.e., I'm going to set up my sample space to be the set of all 23 tuples. So the birthday of the first person, second person, third person, all the way up to the birthday of the 23rd person, such that the xi are birthdays. Right? So I just pretend that I put all these people in order, put them all in a tuple, and then I just line up the 23 birthdays that they have. And of course, I want to know the probability that two people will share the same birthday. By the way, the size of S, we actually know the size of S by a counting principle. So we know the number of ways to create tuples of size R, where each entry has n options, is n to the R ways. And that's by the multiplication rule. Therefore, we actually know the size of S, and it's actually huge. So the n here would be the 365, and the R would be the 23. So it's going to be 365 to the 23 total possible things here, right? Which is a lot. Now we want the probability of, let's call it B, where B is the event at least two people share the same birthday. Now, the size of B, it's pretty complicated, not gonna lie, right? Because what would it mean? Remember, at least two people means 2 or 3 or 4 or 5 or 6, all the way up to 23 people share the same birthday. But even within any one of those, there's so many options, right? So if we look in the case where two people have the same birthday, well, which two people? Well, it could be X1 and X23. It could be X3 and X17. It could be X5 and X4. Could be, right? It could be, there's so many combinations of twos, and then you have to worry about the threes. Okay, well, it could be X2, X7, and X10, or it could be X3 and X14 and X15, or it could be, right? And then you have to do that for 4, and then for 5, and then for 6, and then for 7, and then for 8. Yeah, it's not something that we want to do. So probably here, we would check the complement. Well, B complement is the event less than 2 people share the same birthday. Which in this case, it's like i.e. only one person shares a birthday with themselves, right? That's essentially what that means. I.e., so this is equal to the event no one shares a birthday with anyone else. Now, once you realize that that's what you're counting, that's actually a lot easier than the first situation. So essentially what this means, B complement the size of B complement is actually easier to conceptualize. It's the number of tuples in S that have no repeats, right? So if S is just all the possible lists of birthdays, we just want all the lists where no two of these are the same. We don't want any repeats, right? We don't want December 25th and then another December 25th at some point. So we actually know how to do that. We know how to count the number of tuples of a certain size that have no repeats. In fact, that is a permutation. This is going to be P of 365, choose 23. So out of 365 options, I'm going to choose 23 to put in order without repeats. right? And I already imagine that I'm putting these people in order because I'm putting them in a coordinate. And so now that would mean, well, the probability of B complement is just going to be P of 365 choose 23 divided by 365 to the 23 power, which is the size of the sample space. And so this means the probability that at least two people share the same birthday is just going to be 1 minus that number. And it turns out that that number is roughly 0.4927. And so that actually gives us 0.5073. There is a greater than a 50% chance that two people share the same birthday. Right? And this one actually makes sense, because what you can realize is happening here is that by independence, it means person one and person two and ... person 23 all chose different birthdays. And so what that means, because the and we can multiply the probabilities together, what you'll realize is that, well, person one can choose any of the 365 days out of 365. The probability that the second person has a different birthday, well, he can only choose 364 out of 365. And I can multiply that because people's birthdays are independent. At least they would be assumed to be in a random group. And then the third person can only choose 363 days out of 365. And this continues for 23 times. Which means the last one is going to be 365, and this is going to be 365 minus 23 plus 1. And then you'll end up seeing that the denominator is 365 raised to the 23, because that's what's in the denominator. And then the numerator is actually by definition P365 choose 23. So that makes sense. Even if you were to write it out like this in terms of independence and just say, oh, one person can choose any of the 365 days, the next person can now only choose 364 days, and the next person can only choose out of 363 days, and et cetera, and you go all the way down 23 times, you really end up with P of 365, 23, comma 23. So yeah, you end up with that. There is another way that this is done sometimes, is to just, again, say for any two people to not share. Now, let me phrase that as event any two people D equals event, any two people do not share. So probably the event that two people do not share the same birthday. So the probability of that is going to be, again, person one can choose 365 out of 365 days. He is unrestricted. And then person two, you can multiply by 364 over 365. This is person two. And you can multiply because of independence. One person's birthday shouldn't affect another one. My birthday doesn't change just because your birthday is something else. So you'd realize that just gives you 364 over 365. So now you want the probability that all possible pairs do not share birthdays. Well, again, by independence, this would be something like, well, 364 over 365 times 364 over 365 times 364 over 365 times ... 364 over 365, where it's like the first, this is like the first pair, second pair, third pair, so on. So the first pair doesn't share it, and the second pair, and the third pair, and the fourth pair, and the fifth pair, and the sixth pair, and etc. And that happens for, this is the number of pairs. So that probability would be 364 over 365 raised to the number of pairs. Now, how do you find the number of pairs? Well, you have 23 people in a room. You want to pair them up. And once you put them in a pair, you don't particularly care about the order of that pair, right? You just want to pick those people, put them together, and pick those two people, put them together, pick those two people, right? How many ways can you do that? Well, it's 23, choose two. You want to choose two people out of 23 to compare. So probability that all pairs do not share birthdays is going to be 364 over 365 to the 23, choose two. So this means the probability that at least two people share the same birthday is going to be 1 minus 364 over 365 to the 23, choose two. And it turns out that that gives you that 50.73%. So that's another way I've seen it. Personally, I find the first way a little bit more intuitive, but some people might like the other way, especially if you've practiced a lot of problems with independence and you know, oh, I can just multiply all these probabilities. So just find out the ways that one pair won't share and then multiply that probability by however many number of pairs, and then you figure out that the number of pairs is 23, choose 2, and so you get that. And then, of course, you take 1 minus that to actually get to the answer. Now, once you kind of went through the trouble of figuring out part A, part B is not that hard if you just see the trick, right? So what is the probability that someone in the room has your birthday? So it means now that your birthday is separated from everyone else. So you're one of the 23 people, but now you are separated and your birthday is separated, and now you're measuring yourself against all the other 22 people. So now what you want to see is, similarly by complement, what is the probability that all of the other 22 people don't share your birthday? Which means that you have 22 people choosing from 364 days because they're not allowed to choose your birthday. And once you think of it that way, then either one of the methods that you use, you can just tweak the numbers and get the same answer. So here, for B, we can remove you and your birthday from the group, then see who among the 22 share your birthday. If they the complement is no one shares your birthday. So this means all 22 must pick from 364 days. Right? And so you would get, by method 1, the probability of sharing a birthday would be now 1 minus P of 364, choose 22, over 364 to the 22. It's 47.66%, roughly. So it drops a little bit because you were removed from it. And method 2 is that the probability of B would be 1 minus 363 over 364 to the 22, choose 2. So they don't share a birthday with each other, and they don't share a birthday with you, right? So and so that was the event. So you could do that way. Yeah, it's birthday problem. It's a very famous problem. I'm sure you can find like other ways to do it as well, but I think those are the common ways. So if we go to problem 4, which is the next one that we wanted to do. Yes. So did problem 1, 2, and 3. So we're down to problem 4. A bowl contains 10 balls. 5 are red, 4 are blue, 1 is green. You select 2 balls at random, and you replace the first selected ball before picking the second. So you pick a ball, then you put it back, then you shake it up, and then you pick another one, right? Without looking, what is the probability that both of them were green? Or the probability that both were blue? The probability that both are the same color? Or the probability that both were different colors? So you pick one, you look at the color, you put it back. You shake it up, you pick another one, you look at the color, you put it back. What were the chances that you chose the green one both times? Or you chose the blue one both times? Or a blue one both times? Or you chose a red one both times? Well, that would be for the same color, right? So that's what we're doing, right? You're just picking at random. This is called sampling with replacement. And here, independence is assumed. Right? Because you pick one and you put it back and then you just shake it up and pick again. Your first choice has no effect on your second, right? It will not influence the second because you put it back, right? So it's like you were starting all over, right? One won't affect the other. So you can actually assume independence here. And independence would tell you the probability of something occurring and something else occurring, if they're independent, it's just a product of the probabilities. We looked at that last time, or the time before, maybe. So we can use that to our advantage here. So it's a very well-known kind of setup where you're just choosing things, but you replace them before choosing something else. It's called sampling with replacement. So we can look at that. And so here we can say note there are 10 balls. This is the total number of options. So we know that that's going to be in the denominator. And then we have 5 red, 4 blue, 1 green. Okay, now you think of a probability, both green. So what you can do is you can think of this as the probability that the first is green and the second is green. And because of independence, this just comes down to that. So now we can just do that. What's the probability that the first was green? Well, there's 1 green out of 10 things. So it's 1 out of 10 times 1 out of 10. So there's a 1% chance that you will choose green both times. Both blue. What are the chances that you pick both blue? Well, it's a very similar thing. A probability that both blue, well, that would be the probability that first is blue and second is blue. So that's going to be the probability first is blue times the probability second is blue. It's going to be something over 10, something over 10. And blue, there were 4 of them. So this is 4 and 4. So that's 16 out of 100. There's a 16% chance that you'd pick blue both times. Probably the balls have the same color. So if we move on to C, probability of same color. Well, this would mean the probability that both blue or both red or both, why did I type out red? Or both green, right? And here we also have that they're mutually exclusive because you can actually have both of these occurring at the same time. Why? Well, you can't pick two blues and two R's because what that would mean is you made four choices, right? And you can't pick blue two times and then R two times and then green two times because that means you made six choices. Like they can't happen together. You either make the choice where you got two blues in a completely different universe, completely separate. You chose two reds, completely different universe, completely separate. You chose two green. They couldn't occur all in the same experiment because you would have made more than two choices. So that means we can actually add the probabilities. So this is both blue plus both red plus both green. Now, both blue and both green, we already know that. So both blue was 16 over 100. Both green was 1 out of 100. But both red, we can actually do a very similar to what we did above. And red, there were 5 of them. So you could have gotten 5 choices out of 10 in the first situation, and then get that again in the second situation. There's actually a 25% chance that you would have gotten both red. This ends up being, I think, 42. So there's a 42% chance you would actually get the same color. Well, it's probably that you'll get different color. It's probably a different color. Well, getting a different color is just the opposite of getting the same color, isn't it? So this is just 1 minus the probability of getting the same color, because that's the complement of different color. So we would have, well, it's 1 minus 42 over 100. So that gives you 58 over 100. So that's sampling with replacement. You have the total options. You just count the number of ways you can get the option you want. You can just multiply it by the other ones because you can assume independence here. Now, in the other case, in problem 5, you had to repeat without replacement. So this is called sampling without replacement. Here you don't have independence, but paradoxically, this is one situation in which you can still do that multiplication idea, except things are going to change a little bit. So I want you to recognize that this is the dependent case. Because, for example, if you pick the blue first, you now affect the chances of you getting a blue second, right? So picking a blue the first time, you have a 4 out of 10 chance of getting that blue. But now, if you don't replace it, all the probabilities change because now you're choosing from a group of 9, and only 3 of them are blue, right? So the probabilities will change. However, conditional probability can give us a similar result as with independence, but we change the size of the sample space as well as the choices. Now, how that would work is that I can show you an example. For example, what is the probability that the second is blue given that the first was blue? Right? So that would be the probability that the first is blue and the second is blue divided by the probability that the first is blue. And so what you can recognize here is that the probability that the first is blue and the second is blue is just going to be the probability that the first is blue times the probability that the second is blue given that the first was blue. Right? And you can actually do, instead of blue, blue, you can do this with any two colors. This would actually still be true. So you could actually find what is the probability that the first was blue and the second was red or something like that. This idea would still work, right? So now to go to A, probability both blue. Well, that's just the probability that the first blue and second blue, which here we know by the above is going to be the probability that the first is blue times the probability that the second is blue given that the first was blue. Probably that the first one was blue, there are 4 options out of 10. Now, given that the first was blue, it means now there are 9 options, and only 3 of them are now blue because you got the blue in the first one. So we now have that. So this is 12 over 90. That would be the probability in the without replacement case. This is sampling without replacement. Again, it's a very common scenario. So I'm just showing you how we deal with this scenario in a probability context. You'll get that. So the denominator just changes with each choice. That's going to be it, because you're now not replacing anything. A was probably both were green, so I just did B. Can I move this down? Now, the probably both are green should be a little bit obvious, I think. I think probability both green. Well, I mean, it makes sense this is 0, right? Why? Because there's only one green and you're not replacing it, which means if you pick the green, it's now removed from the box. What is probably that you're going to pick a green again to get 2 greens? Well, 0. There isn't two greens. Like it's impossible to pick two greens, right? The probability should be 0. But you can use the same idea of the probability that the first green and second green. And so now you go, well, that's the probability that the first is green times the probability that the second is green, given that the first is green. And of course, the first being green is 1 out of 10. The second being green, 0 out of 9. There are no greens left. That's 0. And D, C. So let's have the same color. So probability, same color, equals probability, both green, or both blue, or both red. This is going to be the probability, both green, plus both blue, plus both red. And again, this is because of mutually exclusive. You don't just randomly add probabilities just because you see an or. Which I think the next example, which I'll leave you guys to do, example 6 and 7, you'll see that come up. So probably of both green, we know that's 0. Probably of both blue, we saw that that was 12 over 90. Probably that both were red is, again, the first is red, then the second is red, given that you chose the first was red. So that's 20 over 90. So this is 32 over 90. And of course, D, probability of different color, is 1 minus the probability of the same color. So that would give you 58 over 90. Now, I definitely want you to try the next 6. It's very typical for me to put a problem like problem 6 on an exam. The others are somewhat toss-ups. But in a probability exam, something like problem 6 would be common. Try these for next time. Yeah, 6 and 7. 7 is actually going to lead us into another topic. Once we figure it out, you're going to realize that I don't want to have to do that every single time. And we're going to come up with a shortcut. But problem 6 is very important because it's a problem like that where I'm going to test whether you really understand what independence or mutually exclusive means. So yeah, we will stop there. So as I mentioned, look out for those times where I meet with your groups. So I'll just send out some times. Maybe I'll do a doodle poll and you guys can select. Just like put group 1 or group 2 or whatever. Yeah. So that being said, that's where we're going to stop today. So went through that kind of fast, but hope you guys will have the notes. You can look through it, make sure you can see the rules of probability that we were talking about being used. And yeah, practice those last two problems on your own. Probably is something that sometimes defies your intuition. So you definitely want to practice a lot. But we will stop there. So thank you for your time and attention. Enjoy your weekend. And I will see you guys in the next one. Ciao.